Okay, great. So we have, these are going to be, these are problem sessions on Zoom. You know, I'll post or send a link. You don't seem to be having any trouble finding it when I have them. All right. So last class, I was getting kind of ahead of myself, trying to do formal charge. So I want to back up a little bit and talk a little bit more about what resonance forms. And remember, we had the NO2 minus example, and we drew the Lewis structure for it. And we came up with this. We're going to get back to that NCS minus example that we ended with, but not there yet. So I want to back up. We actually had two resonance structures. That's what we call them. How we did this structure, okay? Just to do a little review. And I forgot the lone pair. There we go. We had 9 pairs of electrons. If you count up the valence electrons, there's 5 for nitrogen, 6 times 2 for oxygen, plus 1 for the charge. That makes 18. That's 9 pairs. So it turned out we had to make a double bond in order to give an octet to the nitrogen. So we ended up with 2 different ways that we could, 2 different places we could put the double bond. We could put it on the right side here on the right oxygen, or on the left, going to the left oxygen. Now, these structures are basically equivalent. They both have, you know, the same number of single and double bonds. They have 1 single bond between N and O, 1 double bond between N and O, but it's just flipped, okay? This is like if you took this one on the left and you just flipped it, you'd have the one on the right. So they're energetically the same, okay? The thing is that to really truly describe at the NO2 minus ion, you actually need both of these, because it has been determined experimentally that both the bonds in this molecule are the same. They're the same length. They're the same strength. And that can't be true if one is a single bond and one is a double bond. So it's almost like each is 1.5 bonds. But Lewis structures don't let you do that, right? You have to go by the rules. So there are actually 2 structures that you need to think about when you're thinking about the Lewis structure for NO3 minus. And this business about having the 2 electrons of the second bond, of the double bond, that these electrons are spread out over the 3 nuclei, right? So it's over all of the 2 O's and the N, okay? We call that electron delocalization. You will hear a lot about that if you take organic chemistry, because there's a lot of structures that this is very important in. And there are structures where you don't just have one Lewis structure, but you might have several what we call resonance forms. So these are resonance forms. They're sometimes called resonance hybrids. And these 2 are actually equivalent to each other. So in this case, we have 2 Lewis structures that are energetically equivalent to each other, that both need to be considered sort of equally in order to describe this molecule. So these are energetically equivalent resonance hybrids. Okay. Now, sometimes when you're drawing the Lewis structure for a molecule, you find that there are different Lewis structures for the same molecule that are all legal Lewis structures, in the sense that they use all the valence electrons up. They have octets on all the all the atoms, and they have duets on hydrogen. So you might be able to write two different Lewis structures that are both legal, but one, so we consider them resonance forms, but one will be more important than the other because it will be more stable. Okay, so sometimes you can write two different, not equivalent, not equivalent Lewis structures for the same molecule. And in that case, you would want to know which of these is the better structure. And the way to determine that very often is by something we call formal charge. We can determine which is better by calculating the formal charge on each atom. Okay, and there are certain guidelines for what should and should not be true about formal charges. So what I'm going to do is do an example for you. This example is carbon dioxide. Okay, so I want to start by drawing the Lewis structure for CO2 and showing you that there are a couple of different ways of doing this, and one is actually better than the others. There's actually three ways. So we're going to start with the valence electrons in CO2, because those are the electrons you have to play with. Most of chemistry is due to outer electrons. So that's why the valence electrons are so important. So carbon has 4. I know that very easily from the periodic table. How do I know it's 4? Yes, it's in group 4, 4A or 14. Yep. And O is 6 for the same reasons, in group 6A or 16. And there's 2 of them. So it's just 12 plus 4. It's 16 electrons or 8 pairs. Okay, so now which of these atoms will go in the middle? Why? Because it has the lowest electronegativity. It's not because we like symmetrical molecules. That's a bunch of baloney. It's because carbon it has the lowest electronegativity. Okay, so we start by writing single bonds. So we'll use up 2 pairs that way. 1, 2. Then we put lone pairs on the outer atoms first. 3, 4, 5, 6, 7, 8. And we're done. We don't have any more lone pairs, but we have a problem. What's the problem? Yeah, there is no octet on the central carbon. So, okay, no problem. We're going to take one of these and we're going to make a double bond. Okay. So when we do that, this is what we get. By the way, when you have 2 lone pairs around an atom, I don't care if you write them top and bottom. I don't care. You could have put them here and here. It just doesn't matter. Anyway, so we still have this, and we still have no octet here. So what we're going to do is we're going to make another double bond here. So we're going to have C double bond O, double bond O, and now we have an octet on each of these atoms. And so this is a Lewis structure of carbon dioxide. But let's take another look at it, okay? I'm going to put a box around it because that's one way of doing this. But look what I did here. Notice with that little red circle on top, I made a double bond over here, and then I took a lone pair from the second oxygen and made a double bond. What if instead I took another lone pair from this oxygen, the left-hand oxygen? So in other words, when I was at this stage, so at this stage of drawing the Lewis structure, this one, see, I was over here. Actually, I was at this stage. I could have taken another lone pair from here and made a triple bond, and I would have ended up with this. Okay, so this is another legal Lewis structure. It puts octets on all the atoms, and I even could have done this one, right? I could have ended up with and these two are equivalent, right? You see that? It's really the same, just flip. So the thing is, we have these basically essentially two different structures. And we would like to know which one of these is better. You know, these two are basically equivalent. So I'm only going to look at one of them. So we want to know 1 versus 2, which is better. And when I say better, I kind of mean like more stable, because molecules like to be stable. And the way I'm going to show you which is better is by calculating this formal charge. Okay, so let's look at CO2 like this. And we're going to calculate the formal charge on each atom. Okay, so remember now, the lone pairs go with the atom that they're on, right? So we're basically counting up the electrons on each of these atoms, and then we're going to compare it to the valence electrons. If it has more electrons than the valence electrons, then we're going to say it has a negative charge. If it has fewer electrons, it's going to have a positive charge. So okay, this guy here, this oxygen, this is O number 1. Well, it doesn't matter. We have 4 electrons from the 2 lone pairs, right? So that's 4. Then we have, okay, this is a double bond. Every one of those lines is 2 electrons. The way we do this is we take and give one of those electrons to each of the atoms involved. Okay, so if you have 2 bonds, that's 1 electron for each bond goes to each atom, and we're counting up the ones for oxygen. So we have 2 electrons from the bonds. So that's 2 electrons. Add this up, you get 6 electrons. Okay, so now I'm going to compare that to the valence electrons for oxygen, which is how many? 6. And it's the same. So the formal charge is 0 because it's the same. Now, the other way that people like to do this is make a little chart. I don't know what to call it, actual electrons on the atom in the molecule. And then the valence electrons, and then to take the valence minus the actual, and that is the formal charge. So on this O atom, we have actual atom, that's the actual electrons is this. We added up the 4 from the lone pairs, the 2 from the bonds, we got 6 for valence. 6 minus 6 is 0. Okay, so now let's do the carbon. So that was the oxygen. Let's see. Okay, so carbon. All right, so how many electrons on carbon? Remember what we do here. We take 1 electron from each bond for each atom involved. So given that carbon doesn't have any lone pairs, so carbon has 4 electrons from bonds. and 0 electrons from lone pairs because it has no lone pair. So carbon has 4 electrons. Its valence is 4. 4 minus 4 is 0. Its formal charge is equal to 0 because it has the same number. I should write that here. There are 4 valence electrons, so it has the same number. So the formal charge is equal to 0. Or you could do it this way on the chart. And finally, I have another oxygen. But take a look at the second oxygen here. What do you notice about it that we've already done? The second oxygen also has a double bond and 2 lone pairs, just like the first one. So that second oxygen is the same as the first. So the formal charge is equal to 0. Okay, now you notice something else here. If you add up all the formal charges, well, it's pretty easy here. 0 plus 0 plus 0 equals 0. But it is always true that the sum of the formal charges equals the charge on the molecule or ion. So if it's a molecule, all the formal charges will add up to 0 because molecules are neutral. For an ion, they will add up to the charge on the ion. Okay, so if I have a -1 ion, all the formal charges will add up to -1, etc. I'll show you an example of that later. All right, so that's what we have for the first one. If I summarize it here, I'll put the formal charges in red. We have basically 0, 0, and 0. Okay, let's do the other one. All right, so let's do the one that looks like this. Okay, so let's and this will be oxygen 1, and this will be oxygen 2, because now these oxygens are not the same, right? One of them has a triple bond and a lone pair. The other one has a single bond and 3 lone pairs. So they're different. So let's do the number 1 oxygen. And let's figure out the formal charge, okay? So it has 1 lone pair. So that's 2 electrons from lone pairs. And then remember, each of these bonds goes half to one side and half to the other. So you've got 1 and 1 for each one of them. So you have 3 electrons from the triple bond. So you add them up, 2 plus 3 is 5 electrons. Okay, so how many valence electrons? So O has 6 valence electrons. So it has 1 fewer electrons than it had, right? Than it had when it was a free atom in terms of its valence electrons. So what does that mean? What is the formal charge going to be? It has, right, it has 1 less electron than as a free atom. So the formal charge is +1. Yeah. And now I'll show you doing that with a chart. Okay, so we have the atom. We have the how did I put this before? I liked what I did. Actual electrons on atom and molecule. Okay. Actual electrons on the atom in the molecule. Then we have the valence And then we have the actual minus, no, sorry, the valence minus the actual. Which is the formal charge. Okay, so the actual electrons on the atom in the molecule we did as 5. We have 5 electrons to put in there. And then this is 6 minus 5, or plus 1. Okay. Now that's oxygen number 1. Now let's do the carbon. Okay, so how many, it doesn't have, it has 0 lone pairs. This looks kind of ugly, so I'm gonna go back to that. So it has 0 lone pairs, and it has how many electrons from bonds? 4, because there are 1, 2, 3 from the triple bond, and 1 more for 4. So there's 4 electrons from bonds. Okay, and also there are 4 valence electrons. So it's the same number. So what does that mean the formal charge is equal to? It's 0. And here, 4 minus 4 is 0. Okay, now we're going to do the second carbon, a second oxygen. So the oxygen number 2. And again, we have this triple bond. Oops. This is the second oxygen. So it has 6 electrons from lone pairs. How many electrons from bonds? Just 1, right? Because this thing splits in half. 1 electron from the 1 single bond. So there's a total of 7 electrons. So this is the actual 7 electrons. And the valence is 6 electrons. So it has 1 more electron than it had when it was a free atom. So this is 7, 6. 6 minus 7 is minus 1. Okay. So that means the formal charge is -1. So if I draw this thing again, oh geez, I put too many. Should be just 1 lone pair on that. Sorry about that. So if I write the formal charges right on the molecule, you'll see I have +1 here and -1 here. And notice the formal charges add up to 0 because carbon dioxide is neutral. It has no overall charge. Okay, so now we have to think about which one of these is better. Okay, what? What do you mean? Aren't they both 0? What do you mean by that? They add up to 0 for both of the Lewis structures. But in this structure, there is more of a negative charge on the right oxygen and more of a positive charge on the left oxygen. The formal, so does that answer your, I mean?
Yeah.
Okay, so the question is, which of these structures is considered better than the other or more correct, right? So we have the typical, this one, this is, and then we have this one. Well, I guess I should put it on the other side. Of course, there are 2 of these that look like the one on the right. Because, we could have the one flipped with the triple bond on the other side, but the numbers would just flip then, the formal charges. So the question is, which is better? Okay. And this one is better, right? This is the one that has those formal charges of 0 on each of these atoms. Here we had +1 and -1 and 0 in the middle. Okay. So the one on the left really is much better. It's more stable. All the formal charges are 0. So the best thing is to have formal charges of 0 on all the atoms. That's considered the most stable. The one on the right, there's a couple of reasons why. So this would be a reason why structure number 1, if I make this number 1 here, why number 1 is more stable. Is and this one is so the one on the right, number 2, is less stable, but I'm going to actually go into a little bit of the reasons why. Okay, so first of all, notice you have a positive charge here and a negative charge on the other side. Now, what do you know about plus and minus charges? What happens with plus and minus charges? If you had a plus charge here and a minus charge here, that's what they'd want to do. Okay, so it's actually work to keep plus and minus charges apart. Okay, so it's less stable because plus and minus charges attract, and they are separated here. But another reason is we have an oxygen, the left oxygen has a positive charge. Now, what do you know about oxygen in terms of whether it likes having electron density near it or not? You know because of the electronegativity chart and what you know about ionization energy, electron affinity. Oxygen is in that upper corner of the periodic table where its electron affinity is very high. It wants extra electrons. It releases a lot of energy when it accepts an extra electron. So oxygen is highly electronegative. And while an electronegative atom can pretty well accommodate a -1 charge, let's say, it really doesn't, it's not very stable to give an electronegative atom a positive charge. Okay, so it's somewhat unstable. I'm just going to write unstable. To give an electronegative atom like oxygen a positive charge. Okay, so for that reason, the much better Lewis structure is the one that has the 2 double bonds, 2 sets of double bonds. This is the best. And this one, both of them like this, these are resonance forms, true, but they are much more minor. So we use this double arrow for resonance forms, but these I would say are very minor. And this is a major, the most important resonance form by far. Okay. Now, the reason we don't rule out these minor ones totally is because the fact that there is electron delocalization, because that's what really is going on here. The fact that those electrons are shared among all 3 of them does give a molecule more stability. So you can't rule them out entirely. They might be important for a chemical reaction somewhere, but for us, this is really the accepted Lewis structure for carbon dioxide. Okay. So remember, I told you one reason we're doing this is to figure out if you have multiple resonance forms, multiple legal Lewis structures for molecules, which one do you pick? And there are actually these guidelines. So I used some of them with this explanation, but there are some more. So here is your list of guidelines. Formal charges of 0 is the best, okay? But if you have a polyatomic ion, for example, there's no way your formal charges can all be 0. They'll have to add up to whatever the charge on the ion is. So they won't be 0. If there have to be formal charges, the fewer atoms, the better, okay? And smaller magnitude formal charges are better than larger magnitude. So having a -2 is worse than a -1, all right? Magnitude just means, how big the charge is. Adjacent formal charges of the same sign is very unstable. So if you have two negatives right next to each other, they're repulsive. If you have a -1 next to another atom with a -1, they want to repel. So that's unstable. Separating positive and negative charges is unstable. So if they're far apart, they want to come together, just like we saw in that CO2 resonance form. And then here's a very important thing. It is really much better to place negative formal charges on more electronegative atoms, and better to place positive formal charges on less electronegative atoms. So putting positive formal charges on electronegative atoms should be avoided, and it leads to instability, okay? And vice versa for placing negative formal charges on less electronegative atoms. Okay, so given all that, I want to talk a little bit about this NCS example. So if we go down here, so here are 3 different legal Lewis structures for the NCS ion. Let's just make sure we have the right number of electrons. Okay, we have 5 valence, 4 valence, 6 valence, because S is in group 6, group 6A, and it's a negative charged ion, so we have to add 1 more. So that's 16 electrons, 8 pairs. And it turns out that you need to make a couple of double bonds, or you can make double and single bonds, kind of like what we did for CO2. So now we end up with these 3 different resonance forms, basically. And the question is, which is more stable and why? Okay, so I'm just going to give you 5 minutes to calculate the formal charges, if you can, on 1 or 2 or all 3 of these if you're fast. So we're going to come back to this. Remember what you have to do. You got to count up all the electrons on an individual atom. The lone pairs go with that atom, and the bonds are broken in half, 1 electron on each side. Hand it up. Viz is going to hand it in. asking anything, so that's perfect. Can I just, okay, let's take that first nitrogen on the left structure. How many electrons associated with that first nitrogen on the left structure? 6. Exactly. So what is a formal charge? Why do you say that? Nitrogen is in group 5, it's not in group 6. It's got 6 electrons now. It has 5 when it's by itself. It has 1 more now. So it's -1.
We subtract those.
You took a valence minus what it has now. So valence is 5 minus 6 is what you have here. So you have on this one, you have 6 electrons. You have 5 valence electrons. So 5 minus 6 is -1. What about the carbon?
0.
Why? Because it has 4 lines coming out of it. Each one of those lines gives you 1 electron for each atom. And the carbon only gets 1 out of each line. So it's 1, 2, 3, 4. That's it. Carbon has 4 electrons now. It has 4 valence electrons. 4 minus 4 is 0. Okay. What about this guy? Are we in agreement back there? We have 4 electrons from lone pairs and 1 from each of these bonds. So it's got 6 electrons. How many valence electrons for sulfur? So it's 0 is a formal charge. So this is 0, -1, and 0. So these are the formal charges. Now notice they add up. What do they add up to? Yeah, that's not really, of course they add up to -1. The only thing that tells you is that you didn't make a gross mistake. Like if they add up to -3, then you did something wrong. Okay, they add up to -1, which it has to because this is a -1 ion. That's what that negative sign is over there. Which makes sense, right? Because it's a -1 ion. Okay, now let's go to the next structure here. What about that N? Somebody in the back row, tell me, well, how many electrons on this N?
I'm sorry.
You're right about one thing, but yeah, well, you're not in the back row, but that's all right. 5 electrons. Why is it 5? It's 1, 2. That's because the lone pairs completely go with the nitrogen, then 1 from each bond, 3, 4, 5. And it has 5 valence electrons. And 5 minus 5 is 0. And what we do here is we take the valence minus the actual. So anyway, we get 0. So this has formal charge of 0. What about this carbon here? Yeah, it's got half of each of those bonds. Half of a triple bond is 3 electrons. And then there's 1 from the half of the single bond. So it has 4 electrons. It has 4 valence electrons. Valence minus actual is 4 minus 4 or 0. Okay, so this is 0. So what is the sulfur going to have to be here? It's going to have to be -1 because we know the charge on the whole thing is -1. So if you go 1, 2, 3, 4, 5, 6, and then 1 from the bond, that's 7 electrons. sulfur has 6 valence electrons. This thing just doesn't let me erase right away. Like I make a mistake and then I have to live with it for the next few seconds. 6 minus 7 is -1. Okay, and notice the formal charges add up to -1, which they should. That's no surprise. It's no great revelation. Okay, now over here, let's do this one, because this one is a little crazier. What is the formal, how many electrons on that nitrogen? Yeah, do you get that? There's 6 from the lone pairs and then a half of this bond. So that's 7 electrons on this nitrogen, but nitrogen has how many valence electrons? So what does that mean the formal charge is? Right. 5 minus 7. It has 2 more electrons than when it's by itself. It's not really the greatest to have a -2 formal charge. Okay, carbon, again, it's got 4 bonds, half of 4 bonds, 4 electrons, 4 valence electrons. The formal charge is 4 minus 4, or 0, 0. And now sulfur. What is the number of electrons here associated with that sulfur? 5 electrons, half of each of these bonds, plus 2 more. Okay, so that's 1, 2, 3, 4, 5. 3 from the bonds, 2 from the lone pairs. And it has 6 valence electrons. So 6 minus 5 is +1. And notice -2 plus 0 plus 1 is -1. So again, they all add up to -1, but that's like no revelation here. The revelation is that you have, really different situations here. And now we need to use those guidelines to sort of figure out which of these is the better structure. So I'm going to call this number 1, number 2, which it wants to call 11, and number 3. Okay, so first of all, can you tell me which is the worst structure here? Why? Well, okay, we have a -2 and a +1. We have a separation of like charges, which is unstable. But the worst thing really, that's the first bullet point. The second is you have a -2 charge. That's a pretty high formal charge. That's a lot for an atom to bear all on its own. -2 charge on nitrogen. So nitrogen is pretty electronegative, but it doesn't want a -2 charge. But -2 is too much. Okay. -1 might have been okay, but -2, no. And then it also has a positive charge on, so well, sulfur is not very electronegative. So the positive charge isn't so much the problem as the negative charge. It's got a large formal charge. Okay, so there's too many charges there in general. Okay, so structure 3 is the least stable. And it's the one with the least importance. I'm gonna write not very important, not just less. It's really not important. Okay, so now I guess I have to write these structures again because I lost them back there. So let's see, we had structure 1, which was this one. And these had formal charges of -1, 0, and 0. Okay, that was number 1. And we had number 2. Okay, so which is better according to the rules? Yeah, this one is better. This one is the better one. Why? He says because nitrogen is more electronegative than sulfur. And I'm going to add, and so can better accommodate a negative charge. And you have to have a negative charge somewhere in this ion because you have a negative charge overall. In fact, I should be putting negatives on all of these, right? So I should have done that up here as well. Well, I did it up there. Good. So nitrogen is more electronegative, so it's better to put the negative charge on the nitrogen than put it on an atom with a very low electronegativity like sulfur. Okay, so number one is the most stable. Number two is next. And number three is the worst. Okay. I would like to call your attention to a special problem I have, which is this one. I'm going to collect this. So when we meet after Thanksgiving, so you have to draw the Lewis structures. There's two different Lewis structures that are distinct legal Lewis structures, and figure out which one is the better structure and say why. Okay. Now there's just a couple more things I have to tell you about Lewis structures before I move on to the next topic. And these are what we call exceptions to the octet rule. And one of them is not very important and is only important for one atom in the periodic table. And the other one is actually a pretty big deal. But we don't do too much with it in this class. So exceptions to the octet rule. The first is what we call incomplete octets. And the only one of these that I think is important for us is boron. And boron, it's a metalloid, so it's kind of like, doesn't know where kind of it really is. And it turns out that for boron, it's just fine with 6 electrons. So boron is just fine with 6 electrons. So there are quite a few compounds with boron in the center where boron only has 6 electrons, like this. It could have 3 bonds. Look at that, 2 in each, and it's 6 electrons, and boron is just fine with this. So for example, boron trifluoride is this. It has 3 valence electrons. Fluorine has 7. So 21 and 3 is 24. That's 12 pairs. I make 3 single bonds. 4, 5, 6, 7, 8, 9, 10, 11, 12. There's no more electrons. And this is actually the final and accepted Lewis structure right here. So that's really all I have to say about incomplete octets. I'm not going to talk about beryllium. We don't study beryllium compounds in this class. The second thing is a little bit more of a big deal, and I call it expanded valence. Some people call it hypervalent, but I've never heard that term except in the OpenStax book. I don't know, maybe in a previous edition. I call it, and most people call it, expanded valence. And this is only for atoms in the 3rd or higher period. So all of those atoms that we write Lewis structures with, we use for Lewis structures all the time. All the ones like oxygen, nitrogen, carbon, fluorine, things like that, you can't do this with, okay? So this is only if you have atoms that in the third period or higher. And what happens with expanded valence is that you can have more than 8 electrons. And lots of times this it may involve d orbitals. But we're not really concerned with the details. I'm just going to do a couple of examples. Here's one, PCl5, okay. I don't emphasize this, so it's good to know, and it's good to sometimes use for structures to get a Lewis structure that's better, and I'll explain why in a little bit. So it's not all that big a deal. But PCl5, what would you do? Phosphorus is in the fifth period, it's in group 5A, so it has 5 valence electrons. It's right under nitrogen. Chlorine is in group 7A or 17, so it has 7 valence. There's 5 of them, so we take 35 plus 5 is 40. Divided by 2, you get 20 pairs. And the structure is like this. Okay, you make 1, 2, 3, 4, 5 single bonds, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, okay? That is the Lewis structure for PCl5. And there's actually, if you count them, each one of these bonds has 2 electrons. That's really 10 electrons associated with the P, and that's okay with expanded valence. Now, I do want to show you one example where to get the accepted structure, you need to use expanded valence. And that happens a lot when you have sulfur. Sulfur is an atom we use pretty often. So I'm going to show you this example with the sulfate ion. So if you draw the Lewis structure the way you've been taught so far without expanded valence, you would take, and find your number of valence electrons. S and O are both in group 6. So we have 4 times 6, 24, another 6 is 30, plus 2 for the 2 minus here. So that's 32 electrons or 16 pairs. So you do this, sulfur. We did this the other day, actually. 4 single bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can see my computer is going to do something now. Okay. And this is the Lewis structure that we came up with last time. I'm going to put a 2 negative here because I really should. You always should bracket your Lewis structures of ions. But now let's calculate the formal charges on these sulfurs, on these atoms. What is when you have an oxygen with 1 single bond and 3 lone pairs, which all these 4 do have that, what is the formal charge on each of them? How many electrons associated with this? No, you have to divide the bond in half. So it's 1, 2, 3, 4, 5, 6 for the lone pairs. So 3 lone pairs, 6 electrons. And there's 1 single bond, that's 1 electron. So that's 7 electrons. But you have a valence is 6 for oxygen. So what does that make the formal charge on the O? Yeah, so whenever you see an O like that, which a lot of times, especially in organic chemistry and later even in this course, you don't put the lone pairs. You assume that you know, like I would assume that, or the teacher, not me, because I'm in Gen Chem, but this teacher in organic will assume that you know that that oxygen has 3 lone pairs. Otherwise, how is it going to have an octet, right? So that whenever you see an oxygen with a single bond, it's a -1 formal charge. So this has all these have -1 formal charges. So what does that mean the sulfur is going to have, by the way? Yeah, the total has to be -2. So that's going to mean sulfur is +2. Does it make sense for sulfur to be +2? Sulfur has 1 electron from each of these 4 bonds. But sulfur has 6 valence electrons. So 6 minus 4 is +2. So that works. So the Lewis structure, the simple way of writing the Lewis structure, the way we've been taught so far, would put formal charges on every single atom. And it's got a +2 charge on one of them. That's not so good. But sulfur is in the 3rd period. So sulfur gets to do expanded valence. And so I'm going to show you now what the accepted Lewis structure is for sulfur SO4 ion. And if you take, so let's just start with what we had. If I make a double bond there, and I make a double bond, well, actually, I'll do it on top. I don't like when I erase, it really doesn't like it. It just doesn't do it. So I make a double bond here, double bond here. This is legal for sulfur under expanded valence rules, which, okay. So let me ask you, what are the formal charges here? What's the formal charge on this oxygen and this oxygen? They're each -1 because we just figured that out earlier. It's that those two haven't changed. What about the other oxygens? Now, wait a minute. We have an O. Yeah. 1 from each of these bonds. 1, 2, 3, 4, 5, 6 electrons. And it has 6 valence electrons. So that's a formal charge of 6 minus 6 or 0. So these oxygens here have formal charges of 0. And what about the sulfur? When you count up half of each of these bonds, you get 1 for each line. 1, 2, 3, 4, 5, 6, right? So you have on the sulfur, you have 6 electrons and 6 valence electrons. So the formal charge is 0. And that is actually a better structure. That's much better from the point of view of formal charges, because you only have 2 negative charges. You have -1s, so you have only 2 negative charges. You know you're going to have negative charges because this thing is an ion with a -2 charge. Okay, only 2 negative charges. And what's the other thing about where they are? They are on very electronegative oxygen atoms. And oxygen atoms are okay, pretty okay with a negative formal charge. Okay, so, and this is not even the only structure. I could have done those double bonds anywhere. I could have them here or here. I'm not drawing the lone pairs, but these are all resonance forms. Anyway, so that is a more accepted structure. for sulfur dioxide. Not sulfur, SO4 2- sulfate ion. Okay, we are up to 7.5 in the book, and there is really only one thing I want to talk about here, and that is bond energy. And I'm going to spend exactly 2 minutes on it because we're not doing energy in this section. We already did a bunch of that. Bond energy or bond enthalpy. And so what this is I've been telling you all along that it requires energy to break bonds. In this section, they actually give you values for how much energy has to be supplied to break given bonds. So these are the energies required to break a certain bond. And the reason I introduce it to you now is because I want you to know, and I've told you this before, but I'm going to give you some numbers, that single bonds, double bonds, and triple bonds do not have the same strength. That a triple bond is stronger than a single bond, and a double bond is stronger than a single bond. So the bond enthalpy is the energy required to break that bond. For CC is 347 kilojoules. For the double bond, it's much bigger, as you might imagine. More electrons, more tightly held. And so the bond enthalpy goes up. But another thing I want to tell you is that the bond length is also affected. And the weaker bond is the longer bond. So this is 154 picometers, 133, 120. So the more bonds there are between two atoms, the more tightly held are the atoms involved in the bond. And so PM, picometers. That's 10 to the minus 12. I can't erase that, so they're tightly held. So stronger bonds. So if we're talking about the same two atoms, like I can't really compare a CH single bond to a CC double bond. But if I'm comparing carbon-carbon CC or CO, CC single bond, CC double bond, CC triple bond, the triple bond will always be stronger. It will always be shorter. So multiple bonds between the same atom, triple bond is stronger and shorter. Single bond will be weaker and longer. And I wish I had time to do this because we've done things like we know what a delta H is for a reaction. And you can actually estimate delta H's for reactions by figuring out what bonds are broken and what bonds form. And you can do that by knowing what these bond enthalpies are. You can go bond by bond and figure out whether you're making stronger bonds or whether you're breaking stronger bonds, and you could figure out the delta H's, but we don't have time to do that, so we're not going to. So anyway, so no bond enthalpy. So we're not going to cover using bond enthalpies to calculate delta H's for reactions. You can learn that in P-Chem when you take it as a chemistry major in a couple of years. All right. So, Lewis struck that, by the way, the exam will go through this. I don't think I'm having any of this next stuff on the exam, but I'm starting something a little bit new here. I have a little time to do it. So what I want to do is talk about how Lewis structures, they're really pretty, they're great, right? I love Lewis structures. I mean, I just love them to pieces. but they do not give a complete picture of the shapes of molecules, right? They're not so good at giving us the shapes of molecules. And let me explain what I mean by that, okay? So if we take the molecule H2O and you draw the Lewis structure for water, okay? So you have 2 plus 6 is 8 electrons, it's 4 pairs. O, H, 1, 2, 3, 4 pairs. You could draw it like that, and that's a correct Lewis structure. It's perfectly fine. Or I could have done it this way. And this would be perfectly fine as well. So both are correct Lewis structures. So what's wrong with them? Anybody know what's wrong with one of them or both of them?
That's option.
They have the same charges. The charges are fine here. The formal charges on H are both 0. They're 0 on O for both. It's the shape. It's the shape. Okay, so this is showing a 90-degree angle, and this is showing a 180-degree angle. So the one on the right is showing water as a linear molecule, and the one on the left is showing water as a 90-degree molecule. And neither of these is right. That's not really what it is in water. In water, this is what you actually have. You have an angle. This angle here in the middle is actually 104 to 105 degrees. It's not 90 and it's not 180. The actual angle is neither. And you're never going to know that from a Lewis structure. A Lewis structure tells you that all of these things, as long as you put the lone pairs there, that those are correct. So the question is, how can we understand that this angle is not 90 and it's not 180, but in fact is 104 or 105? Why? Okay, and how can we get structures, what the molecular structure or the of any simple molecule is? And so what I'm beginning to show you here is something we call VSEPR theory. It's for valence shell electron pair repulsion theory. And the part that I think is the most important in this name is this electron pair repulsion part right here. And so what this theory is kind of all about, so in this theory, the geometry of a molecule is determined by the number of sort of different regions of electron density on the central atom, because electrons repel each other. So, let's take an example. We have methane. Okay, methane is CH4, and this is what the Lewis structure looks like. Okay, so it has this bond, this bond, this bond, and this bond. And these are what we call, these are 4 regions of electron density. In this case, there are 4 bonds. And you have to imagine that these bonds have electrons in them, and they are negatively charged. And so they don't want to be near each other. They want to be as far away from each other as possible in space. So and you know, it's not limited to the plane of the piece of paper or the tablet I'm writing on. If you take 4 balloons, and here I have a picture of 4 balloons, and you tie them in the center. So I've tied them in the center here. And you can see those 4 balloons are getting as far away from each other as possible, because balloons cannot occupy the same space, right? You can't, they push back on each other. You try to put them in the same space, they repel, kind of like electrons. Well, not really, but you get the idea. So you tie these 4 balloons together, and I'm sure they're going to do this in lab with you when you come back. Okay, so, and if you take and connect, the ends of these balloons, let me try drawing this. I'm not always the best at this, but I got some better pictures down below. So there's the 4 balloons. Now, if you take the end of each one of these and you try tying it together, well, I wanted it in red, but it won't give it to me in red. Just not make a structure. See this structure I have here with a triangle here? And if I go up a little bit, you can see it. It won't let me. God. There it is. All right, good. So that pink little, thing there, this is a tetrahedron. This is a geometric figure called a tetrahedron. And the carbon is in the center of that structure. And the hydrogens are in, would be at the ends of these balloons. That's where the hydrogens would be, with the carbon in the center. And the way we draw this thing, must have done something. No, it's not me. Okay. So like I said, this is the carbon in the center, the hydrogens sort of on these ends. So you have this. So I'm just showing you some of the different ways that we can represent this molecule. So the way you draw it is you have a carbon, okay, in the center, or any time you have 4 groups of electrons with 4 bonds like this, 4 single bonds, we draw a line that's just a regular line to 2 of the hydrogens, and then we draw kind of a line going back and a wedge going forward, trying to show a little perspective here. Not being the greatest artist in the world, I certainly count myself among those. This thing will not move down. Yeah, so just to show you in here, you have a carbon in the center, here's a hydrogen. We have a sort of a wedge coming forward. So I'm just going to show you, like when you were a kid and you were in school and they're teaching you how to draw with perspective. They have like the horizon in the back, and there's the sun setting, and there's the train tracks, and they're looking like this, right? Remember that? Am I crazy? They don't do that anymore? Okay. So you could see that, this is where it's closer, it's wider, right? Where it's far away, you have a narrower sort of trail and goes off into the distance. So that's what this is here. It's kind of like the sideways wedge going back. So this is going back and to the side. And this wedge is coming forward. So you can see that, you know, if you've been struggling like with the math part of this course, because you know, like you're an artist or something, you might like this better, you know. You can draw these tetrahedral structures maybe more easily. So anyway, so when I draw a line that's straight like this, that's in the plane of the paper or in the plane of the tablet. And another H. You could always draw two of them like that, but then you have to draw one that's sort of forward-ish and one that's sort of back-ish. That's about as bad as I could have done it, but yeah, it's a little like this. Anyway, I think you get the idea. And I know we're not all great artists, so I don't worry about that too much. But now what are these angles? Okay, we have these angles here. What are they, you know? And it's the same angle, all of these, 1, 2, 3, 4, it's all the same angle. And this angle is called the tetrahedral angle. And it is 109.5 degrees. So each one of these is 109.5 degrees, a tetrahedral angle. So if we go and look at, so this is just more illustrations of the same thing. You can see it in slightly different ways. These angles are all 109.5. So they're a little bit bigger than a 90-degree angle. It's about 20 degrees bigger than that. So whenever you have 4 groups of electrons on the central atom, you will have the same, we call this the electron geometry is tetrahedral. So when you have 4 groups of electrons on the central atom, this produces what we call an electron geometry. In other words, a geometry determined by those electron groups that is tetrahedral. And it's based on that tetrahedron that I showed you before. Okay, so in the case of methane, we have 4 groups of electrons, and I could, by the way, put the wedge on the other side too. I don't have to put those single lines to the left, right? This time I put the single line to the right, you know, the normal line. Okay, so here in methane, you know, all 4 of those groups of electrons are bonds because there are 4 single bonds. But it doesn't have to be that way. There are other possibilities. So let me show you what the other possibilities are. For 4 groups of electrons on the central atom. So maybe we could sort of try to think about them. So we have our methane example. We have our 4 single bonds. That's SB. Okay. But what about this? We could also have a lone pair and 3 single bonds, right? That's also 4 groups of electrons on the central atom. I'm going to draw that one here. And we could also have water, right? With 2 lone pairs and 2 single bonds. So here we have 2 single bonds and 2 lone pairs. In the NH3 example, we have 3 single bonds and 1 lone pair. And then we could also have in HCl, for example, we have one single bond and 3 lone pairs. And they all have the same overall geometry as determined by those 4 electron groups. So I already drew you the methane example. Here's the NH3 example. I should draw that a dotted line going back, sideways lines. And then you have this lone pair, okay? So that's that example. Then I could have oxygen in the middle. And I could have a lone pair here and a lone pair going this way. And then I have my bond coming forward and going back. And then I could even have Cl with 3 of these lone pairs. I'm drawing the bond on the right because that's what I did. Okay, so they all have the same tetrahedral electron geometry with 4 electron groups on the central atom. Okay. So all 4 have an overall tetrahedral electron geometry, but they are not all 4 the same shape, okay? They're not the same molecular structure because the structure of a molecule depends on where the atoms are, not really where the lone pairs are, right? So for example, for the NH3, we're really only concerned with, this would be the structure of the molecule. It doesn't have the lone pair, right? So we have different categories that we put these things in. So for methane, for example, here's our methane again, HH, fix that a little bit, with the 4 single bonds. Oh. Okay, if we have, okay, so in the case of methane, we have an atom is at the end of every one of those electron groups. Thanks. Except now I'm trying to write and there's no eraser. It still doesn't work. So here you could see that the molecular structure is also tetrahedral. The molecular structure is determined by the positions of the actual atoms, is also tetrahedral. But let's look at the ammonia example here. We have a nitrogen with a lone pair, right? Then we have these 3 hydrogens. And if you look at this part here, that is not tetrahedral, right? Because you don't have an atom at the end of that lone pair. So what is that? What is that structure? It's like a little pyramid with an N here and the H's here, which is not the greatest drawing, but if you look at the one above, it's actually not a bad drawing, the pink thing. You could see that it's a little pyramid here. So we call this molecular structure trigonal pyramidal. Trigonal because it's a pyramid with 3 points on the bottom, the 3 hydrogens, And then you have the nitrogen up here, so it makes a little pyramid to those 3 nitrogens. This is a terrible drawing. No, it is not. Well, I'm not much of an artist. That's why I have the pink thing. So it's a little pyramid, okay? So this guy, NH3, has a tetrahedral electron geometry, but it has a trigonal pyramidal molecular structure or shape. Okay. And then we have the oxygen one. So we have now, so here, the top and one of the sides, there's no atom at the end. So where does a shape come from? It just comes from the positions of the atoms. So this again has a tetrahedral electron geometry because it does have 4 groups of electrons, but we say that the molecular structure or molecular geometry or shape is bent. Because that's what it is. It's just bent. Okay. So the HCl I tend to leave out because you only have 2 atoms here. And it could be nothing but linear. So the ones with 2 atoms are pretty easy because there's no argument. It's not going to be anything else but that. So if you look at your packet that I gave you, you have this sheet there. And what this does is it puts it all together. But we start here. We start with 4 groups. We sort of do the hardest one first. Okay. So the 4 is for the number of electron groups. That's the number of groups of electrons on the central atom. That's this 4 here. And that's when you have like a 4 balloon example or analogy. And then it says bonding groups. So these are bonding groups. These are lone pairs. And these are the different molecular geometries, or your book calls them molecular structure. I tend to call them shape. Okay, so when you have a tetrahedral electron geometry, which you have with 4 groups of electrons, you can have a tetrahedral shape where you have an atom at the end of each of those electron groups. You can have a trigonal pyramidal geometry with an atom at the end of just 3. In other words, you have 3 single bonds and you have a lone pair here, which doesn't really contribute to the molecular structure. And then you could also, if you have 2 lone pairs and 2 bonds, you can have the bent shape right there, as in H2O. So this is the first one we do. This is the worst one. We don't do 5 and 6 electron groups in this class. I skip those. So there's quite a bit in the book that you won't have to do. In fact, figure 719, we're just doing 2, 3, and 4, not 5 and 6. And skip entirely figure 720. So you're going to skip all those different ones. The hardest one we do is the tetrahedral case, where we have 4 different, well, 4, I didn't put in the linear one with just HCl. Notice arrangements with just 1 group of bonding electrons have been left out because they're when you have linear, it has to be, when you have 2 atoms, it has to be linear. So we have these three different things here. Bent, trigonal, pyramidal, and tetrahedral. So you notice if you look here, or what I told you at the beginning, in H2O, the bond angle here, I said was 104 to 105 degrees. And here you notice in ammonia, it says less than 109.5. So what I would just like to talk about a little bit is the bond angles that come about from these different molecular structures. So let me just draw them again. We have the methane. We have the ammonia example with the 3 hydrogens in a little pyramid. Doesn't matter, forget it. And then we have the water, 2 lone pairs and 2 hydrogens. Okay. All right, so here, remember I said that this angle is 109.5 degrees, and they're all that way. But here in ammonia, these angles here are slightly less than 109.5. They're about 107 degrees. So why do you think they might be that way? What does that tell you about what takes up more room, a bond or a lone pair? If these angles in ammonia are all squeezed down a little bit, they're a little bit less than what they are in methane, it's because this lone pair is taking up more space and kind of squeezes down on the rest of the molecule. So the lone pairs do not have nuclei or atoms at the ends of them, right? To sort of rein them in. So they are wider. They take up more space. And therefore squeeze down on the remaining bonds. So the HNH bond angle is about 107. I write it as less than about 109.5. That's one way of writing it. I don't expect you to remember 107. I just expect you to remember that it's less than the tetrahedral angle by a little. And in water, we have 2 lone pairs that are taking up more space, pushing down even more on that bond. So this bond here is about 104 to 105 degrees. So it's even a little smaller, less than about 109.5. And it's a little smaller than the HNH bond angle. And about bond angles, I would say that, what you need to know is that a bond angle is the angle between 2 bonds. So this we would call the HOH bond angle. Okay. All right, I just want you to take a look at the exercise that I have next, which where I was hoping we would get to a few of them. So maybe you could look at some of these. We'll start with this. CH3F is one. NH3, which we really just did. H2S and CCl4. We take a look at the first one of those. It's in the packet. It's the last thing in the packet. I'm not putting this geometry on the test. Like I said, I stopped before that. So if we draw the Lewis structure of CH3F, We count up our 4 electrons, 3, 1 for each hydrogen, and 7. That's 14 or 7 pairs. And then this carbon goes in the middle. So you just start by drawing the Lewis structure. Okay. And you put 1, 2, 3, 4. And then you put your 3 lone pairs here. And so this is the Lewis structure. So then you're asked to count up the electron groups. What are the groups of electrons on the central atom? How many are there? And you see here that you have 1, 2, 3, 4 electron groups. And we've only learned about 4 electron groups. So the electron geometry, which they also call the electron pair geometry, but it's the same thing, it's just the electron geometry, is what we call tetrahedral. And the molecular geometry, now that's determined by how many of those groups are bonds. And here we have 4 single bonds. So we have an atom at the end of every one of those groups. So when that's the case, that you have 4 electron groups and there's an atom at the end of each one, then the molecular geometry is also tetrahedral. Because you have atoms at the end of each one, and those atoms determine what the molecular geometry or molecular structure is. I'm going to give up, okay? What is the bond angle? 109.5. Okay. How about H2S? Why don't you guys do this Lewis structure of H2S? It should look very familiar. Oh, it's not 8 pairs, it's 8 electrons. It's 4 pairs. It's really just like water. Because S is right under oxygen. But again, it has 4 electron groups. So its electron pair geometry or its electron geometry is just tetrahedral. But in this case, we only have single bonds to 2 atoms. So we have a bent structure here. And that makes this bond angle less than about 109 degrees. So that's all I wanted for this part. Because these count, lone pairs count as well. Because even though they don't have atoms at the end of them, the fact that they are there taking up space means that the overall geometry is tetrahedral. Okay, and that's what causes the angle to not be 90 degrees, as I may have shown it here, but to be a little bit less than 109.5. So you really should draw it like this. Just like water. All right, that's enough. Have a good holiday. Hope you eat a lot of turkey and don't get sick. I won't be in tomorrow. I probably won't be in this afternoon either, but I don't think any of you were planning to come. If you were, let me know. I hope you have a great time with your families and all that. Study when you finish eating.
Exam, the paper. I just didn't grab it.
Your own paper?
Yeah. No, the new one.
I don't understand what you want.
There was an exam with the paper.
Oh,
I
yeah.
didn't grab it.
Oh, sure.
I was like, I just need the paper. You were like putting it away. Okay.